Dirac Calculus at Arizona State University. I want to give you a brief tour. The project was Dr. Pat Thompson, PI, and Dr. Milner and I, co-PIs. So let's just quickly talk about the origins of Dirac. I'm going to go in and out of my presentation, so I'm just going to sit, if that's okay. All right, so origins of Dirac. And in 2010, Pat Thompson piloted a from-scratch redesigned Calc 1 course. And the goal was to make calculus meaningful and relevant for students. And it shifted focus from performing procedures to modeling covariation through rate of change and accumulation functions. So he had about 3 semesters of iterations, and he handed it off to me, and then we continued to iterate and revamp and revise. And then we gathered some really positive data about the curriculum, and so then we were granted the Dirac Nsf Grant. It was a 2-year grant in 2016. And so DIRACC stands for Developing and Investigating a Rigorous Approach to Conceptual Calculus. So I'm going to go through some key features of the curriculum that you can keep your eye out for as I go chronologically through the course. So I'm going to tour you chronologically through the course, but before that, I'm just going to kind of point out these are the key features. And the first is that we're going to model real-world covariational relationships through rate of change and accumulation functions. This is really the meat of it. We're going to sequence ideas cohesively, building to an end goal. It's not going to be section 1, do these problems, section 2, do these problems, disjointed. Everything is building on what we've done before, and the goal in the end is the fundamental theorem. Whenever we introduce a new topic, it's going to be in a real-world context. So applications are not the afterthoughts, but from the start. Everything's going to be introduced in real-world context. Ahead here. And so then we're going to emphasize symbolic representation, and especially function notation. And we do that at the beginning of the course. We really work on function notation. Their skills at understanding and using function notation are really poor. They think function notation is just like something you're supposed to do, plug and chug, right? But function notation is representation, so we work on that. Differentials, dx, are actually variables. We're going to treat dx as variables, and those are going to vary through fixed intervals delta x. We're not going to treat limit formally. We're not going to go through the whole limit sections and do limit problems, but we're just going to treat it informally as approximations are getting so close to one another that we can't tell the difference anymore. So we're going to just call it a day and say that they're essentially equal. We're going to distinguish between open and closed form of rate of change and accumulation functions. And then a big part of the course is something called graphing calculator. It's kind of an unfortunate name because it's something much different than a handheld graphing calculator. It's computer software that you'll see lots of examples. We're going to use that in class for both didactic objects or like centerpieces for having a discussion and talking points. And then also students have graphing calculator, the GC software, and lots of their assignments they're going to have to be using the GC and building their own animations. Okay, so these are the key features. So let's go through a brief tour of the curriculum, and before we start, there's this course theme to the course, and we repeat this over and over again throughout the course, and that is this, that all of calculus is about 2 foundational problems. You know how much something you have, how much of something you have at every moment. You want to know how fast it's changing at every moment. That's half of calculus, and the other half is you know how fast something is changing every moment. You want to know how much of it you have. So this is kind of our mantra for the students. We're repeating this over and over again. Okay, what are we working on now? Is it endeavor A or is it endeavor B? Okay, so we start with some pre-calculus topics. We introduce them to the graphing calculator GC. I'll show you in a moment. Really work on function notation with them, not as a plug and chug exercise, but as representation of dependent variables of a function. We have to work on them as the concept of amount of change in a variable. So they're not very good at variables varying, but they're much worse at thinking about a variable as being the amount of change of a variable. And so we work on that. Okay, so the first assignment that they have for GC is this one here, and it brings together, representing a function. This is the expected attendance at a football game based on temperature. So expected attendance being the dependent variable, temperature in Fahrenheit being the independent variable. And so there's a kind of 4-page worksheet that leads students through building this GC file. And so it consists of defining that function. Points are in vertical matrices, not horizontal ordered pairs. But the great thing about GC is it's not a computer program where they're doing computer programming. They're learning some language. The language of GC is mathematics, precise statements of mathematics that if they put them in correctly, the software will display the correct animation. So in this one, n is a variable that you can vary on a slider here. And so they're creating this. So based on the function a, they're creating this animation. And so it forces them to show these changes, this change in independent and this change in dependent, and this little triangle. It forces them to use function notation to do that. So for instance, this vertical change right here, this is representing a change in expected attendance. That's this statement right here. So it's all the points where x is n plus 10, and then the y values from the original function value to the function value at n plus 10. So they can't get away. There's no way they can build this without knowing and using function notation. Okay, and so then next thing we do is we really work on constant rate of change. Constant rate of change is the bedrock of accumulation functions. This is the underlying principle, so we really work on this hard with them for a week or two. And we're going to frame the meaning of constant rate of change by this differential relationship, that dy equals m dx. So what does the constant rate of change m mean? We frame that with dy equals m dx. So throughout the presentation, I've inserted slides that I'm actually using in class. So this is one of the slides that we actually use in class. And so suppose you're cruising at 70 miles per hour. What is the meaning of that? And most students will say, for every hour that you go, you're going to travel 70 miles. And what we say is that's a really narrow meaning. That's a very narrow meaning of that constant rate. And that really, so you also know more than just how far you go in 1 hour. You know how far you go in 2 hours. You know how far you go in 5 hours. You know how far you go in a half an hour, a tenth of an hour, etc. So really, for any change in time, this constant rate tells us what the change in distance is by multiplying it by that change in time. So this is, again, this dy equals m dx is foundational here. And it tells you more than just how much change you get for one unit of change. It tells you how much change you get for any unit of change. So for any change in time, the change in distance is 70 times the change in time. And this takes, for some students, 2 and 3 weeks for them to get this. They watch the slide and go, oh yeah, sure, that's easy. When you ask them to apply it, it takes a lot of time and practice. Okay, another assignment we have them do, and this is kind of practicing now constant rate of change is kind of a second assignment they have them do. So this is minutes gone by in class and your laptop battery percent. And so here the variable is dx, and it's the change from 35 minutes into class. And so given different values of dx, they're showing the corresponding change in your battery percentage. And so that battery percentage is similar to the last one. That change in battery percentage is, here's that mathematical line. Again, it's not a programming language. Students have to come up with the mathematics and enter it precisely to have the animation or the visual show up correctly. And so here, again, this is forcing them to use constant rate of change. That change is going to be 41, the original amount, plus the change in the battery percentage, and there's the MDX right there. So again, giving them practice with this concept of dy equals mdx. Okay, the next thing in the course is we talk about what we call a moment, and it's like warm up and practice for when we jump into the calculus. So we're kind of knocking on the door of the calculus here. We say a moment is a small interval for which the rate of change is essentially constant, and inside the moment, dx can vary within the moment. And so we're going to continue practicing in representation constant rate of change. So this, we use this application here. This is Usain Bolt's 100-meter world record. And we show this is his distance, and you see it's a changing rate. So by looking at a moment around 1 second into his race, we're assuming a constant rate. And then within that constant rate, we look at changes of x dx and the corresponding change in distance according to dy equals mdx. And so this, this context, we have the students practice identifying values from the setup, and then representing those values symbolically. So like the initial value of the independent variable is 1 second, symbolically x initial. The final value, or the initial value of the dependent variable, 3.482, symbolically function notation, f of 1. Differential of x. So we emphasize that dx varies, but here we're looking at a particular example where dx is 0.006, differential in f, 0.0368. The moment in question where we're assuming a constant rate, and then the rate of change. So again, just getting students to read the context and symbolically represent the situation that's going on here. And here's another variation of that. This is around 0.4 seconds. This is a little bit different here. I'm giving the rate of change and asking them to, the rate of change is m, and that's given in this problem. So key values of the independent variable, x initial and final, the differential. So the differential in the dependent variable can be represented two ways, df and mdx. Initial distance from the start and the final distance from the start. And so here we're really knocking on the door of accumulation here. Initial value plus the change. So again, giving students practice and representation before we jump into the heavy-duty calculus. Okay, and so then we're ready to start introducing accumulation from rate. And again, this was one of our endeavors. You know how fast the quantity is changing at every moment. You want to know how much of it you have at every moment. And this is in contrast to most traditional calc curriculums that work on derivative first. So we're going to work on integral first for several reasons. One being accumulation is kind of a more intuitive concept. And this dy equals mdx, really, it sets the stage for the whole calculus course. So a moment now is a fixed, largish delta x interval. And given a changing rate function, we're going to build a pretend rate function of constant rates in order to apply the dy equals mdx. And then from that, we're going to build a piecewise accumulation function from that pretend rate function using those constant rates. So that y final equals y initial plus mdx. So here's kind of an overview of that. So again, you know how fast something is changing at every moment. You want to know how much of it you have. So you know how fast something is changing at every moment is your given rate of change function. And so from that, our goal is to build both net accumulation function tracking changes in the quantity and the total accumulation function, which is tracking total accumulation of quantity. So just setting the stage for what we're doing. So here's a new context that we bring in, and this is an oil spill. So number of days being independent and the volume of oil that has spill in the ocean. But so the rate of change of oil entering the ocean is here given. And so our goal is, given this exact rate of change function, to derive or come up with the accumulated volume of oil, leaked at any number of days after it began. And so this is kind of so you know how fast something's changing every moment. You want to know how much of it you have. So here's kind of an overview of the key to doing that. So given meters cubed per day, we're going to use constant rate of change. The changes in volume are the rate times changes in time. And then we're going to say that any accumulated volume is going to be some initial volume plus the change. So again, this is the whole embodying the kind of it's the nuts and bolts behind this endeavor here. That given the constant rate, we're going to be able to calculate a little bit of accumulation and calculate a net or total accumulation. Again, the white slides are the ones that I'm actually pulled from using in class with the students. So here's that oil spill. So we need this pretend rate function based on constant rates. So we're going to use function notation to represent particular actual rates. And then we're going to build a pretend rate function of constant rates so that we can use dy equals mdx to build the accumulation function. So this is a new function created from the actual rate function that approximates the RV. And a question that I ask over and over again in this section of the course is, if we've got the exact rate of change function, why do we want to make it worse? Why do we want to make this approximate rate function that's not as good? I ask that question over and over again. It's because constant rate of change allows us to build accumulation. And so we're gonna write that approximate accumulation function piecewise, and then we're going to write it. Then we're going to use that to write a piecewise accumulation function. So here on the screen, I'm drawing with my scribble pen to finish the screen. So the next, another example of this same thing is our basketball rocket context. And so there's it's a basketball that has rocket powered, and it has boosters that boost it to the next rate every, in this case, 0.9 seconds. And so this is kind of where we're at in the course. We've got this constant rate piecewise function, and we want to build in this case the approximate height of the basketball as a piecewise function. So this would be an example of a GC file that I would use as a discussion, a center of discussion in class. But this is a little bit beyond what students can build at this point. So based on that basketball rocket example, we've got the approximate rate function, and that's just going to be constant rates over intervals. And based on this now approximate rate function, we're going to build the accumulation function. And that accumulation function is, each piece of that is initial value of height plus the change. Initial value of the height, and that change here is our mdx, right? So it's m times change in the independent variable. Okay, but you can imagine what would happen when we make the interval small. This is not very practical at all. You're going to have as many of those pieces as you have intervals. And so this is a great way of getting the idea of the approximate accumulation function, but it's not our end goal. So what we want to write the piecewise accumulation function in one rule. We want to, instead of writing it in multiple rules, we want to write that in one rule. So we want to distinguish between completed and current intervals. We want to use the floor function to count the number of completed intervals, and we're going to build the left function, which gives the starting x value of the current interval. And then from that, we're going to construct our approximate net accumulation function. So the idea that so as time is increasing, time is a variable, as it's increasing, if you pause time, in this case time in seconds, there's going to be some number of intervals that have been completed, and then there's going to be a current, in the current interval is going to be a partial change. right? And so the completed intervals are of width delta x, that's fixed. And then that little change in the current interval is dx. So that's our variable. Dx varies through the current interval from 0 to delta x. So we're summing up the change from the completed intervals, and then we're going to add on the change from the current interval. And we want to develop a one-rule function that does that. So here's a GC file that we use in class to help them. We've got lots of the symbols flying around now, and so again we got to practice representation. What is everything about here? So here's not that one. So here's a file where we use in class as a quiz, where we're asking them to identify all these different quantities and objects. And so I can set this to run. So we can let x increase, and then in this GC file, we can go through and say, okay, what is, say, this quantity right here? Well, that's question 1. That's not showing up here. There, that's x. Oh, that first question was the starting value of our accumulation, and then second question, that's our value of x. This is dx. It increases through the current interval. What just popped up there? Oh, this is delta x. Those are our width of our completed intervals. Those are the completed intervals. Jumping around on me. That's the current interval, where the value of x is increasing and dx is increasing. There's this function that we develop called left x. That gives the value of x at the start of the current interval. And then the red function is the exact rate of change function. And then the black step function is our approximate rate of change function. So this is there's a lot of symbols and language flying around. So this animation really helps students to nail down what everything is. And before we get to this kind of complicated and scary one-line accumulation function. And I have one slide to show that. This takes 2 days of class to go through. I have one slide. I'm going to show it to you in about a minute. So how much do we have at any current value of x? Well, it's the accumulation due to completed intervals. M dx plus M dx plus M dx plus M dx. Those are the current intervals. And so that we can use summation notation to represent that. Plus the additional accumulation in the current interval. And that's where the left comes in. So that's going to be the rate at the left side of the interval times dx, that value that's varying through the current interval. So how many completed intervals are there? We need the floor function for that. And then what is dx in terms of x? So that's going to be x minus left of x. And so this is the one-line accumulation function. And we're getting students to understand this. And there's lots of practice. We ask all kinds of questions from different angles, and we have them work in GC. And they have to type this out and get all the semantics correct, precisely correct for it to work in GC. What was I going to say? Oh, but so you notice how much function notation is going on in this one function, right? So there's the approximate rate function. There's the left function. Here's the approximate rate function again. And the function itself, a of x. So again, emphasizing how important function notation is. Okay, and so then the next context we look at to practice that is the sand unloading. And so Oh, now it works. I've been having trouble with the smoothness of this. But anyway, so here's our exact rate of change function. And so we have in-class worksheets where we're asking all kinds of questions as they're watching this animation on the screen to really understand it. So from the exact rate of change function, we build the approximate rate of change function. That's our step function. And then from that step function, we can build the approximate accumulation function, and I'll repeat it here up here. So there it is. And so this idea of you know how fast something is changing at every moment, you want to know how much you have at every moment, is really a sequence of 4 functions. It starts with the exact rate of change, and then we build the constant rate of change with a pretend rate function, the blue one. From that, we can use the one-line accumulation function. And then the last function is the exact accumulation function. And so when you ask the question, how are we going to get the exact accumulation function? It seems like it's an easy question for the students. So we're going to make the interval smaller. And so the beauty of GC is I can just come up here and click delta x. I can click it and make it smaller. And it changes it'll change the rate function, the approximate rate function, and the approximate accumulation function. I can make it smaller again. And so we're thinking about the idea of limit here. And so now I'm only showing the approximate rate function, but it's looking a whole lot like the exact rate function. So here's a delta x of 0.006. And so we use the idea of limit as these approximations are getting so close to one another that they're essentially indistinguishable from one another. And so then when that happens, we have the exact accumulation function. So we have a whole series of questions around this animation in class and for homework that we're asking them to get this idea of the sequence of functions that allows us to write how fast the quantity is changing given the rate of change. Okay, and so then the exact net accumulation function is our integral function. And so like we just did, we make the interval small. And then we stop when the approximations are essentially indistinguishable. We call it a day and call that exact accumulation function. And then we're going to introduce the integral function notation as a concise form of this ugly a function just when intervals are small enough. So we want to think of, so we introduce integral notation here, and we're going to think of that as this. It's really the same thing as this, with a small enough value of delta x so that values of a are indistinguishable from exact accumulation. And so then this partial interval really has no contribution. It's like they're all super small intervals, and so the partial interval, we can really just get rid of that. And then we ask them to see, how are these the same? So how are these the same? So this is what we're doing. We know how fast something is changing, so we start with the rate function. We want to know how much of it we have, which is found by summing up. So Greek sigma is for our approximate accumulation, and then we use German S, which also means sum, for exact accumulation. By summing up bits of change, so again, we said constant rate of change is the bedrock of accumulation. Here it is, m dx. Right? The rate times the change in x. So with an integral function, the dt or the dx isn't just telling you what variable we're using. It's part of the math, right? It's the rate times the change. There's a big conception out there. I even saw it in a high school math publication where, you know, the little dx is just telling you what variable, right? It's telling you what variable we're integrating with respect to. No way, it's part of the math. It's multiplication. M times dx, constant rate of change. From the starting value of x to the current value of x. So this is our transitioning from that one-line accumulation, approximate accumulation, to our concise integral form for exact accumulation. So here's our sand unloading again, and so there's the approximate net accumulation, and so now that we have exact net accumulation, and then we can start talking about total accumulation, which is pretty easy from exact net accumulation. Suppose if the scale already had p100 pounds of sand on it, then what would the function f be, the total number of pounds? Well, it would just be p plus the amount of change, the net accumulation. So here we're dangerously close to the fundamental theorem here. So all semester we've been working on this, and this is really just the fundamental theorem in disguise. So then we embark on the reverse process. You know how much of a quantity you have, and you want to know how fast it's changing. So we're going to begin with fixed intervals of delta x, but then we're going to consider all intervals of delta x, starting from every x value. And we're going to change the notation. We're going to use h to represent x, delta x, which is like traditional calculus. So what we did, here again, our progression of 4 functions from exact rate of change to approximate accumulation to exact accumulation. And we did the heavy lifting. So if we had the exact rate of change, now we can just write down the exact accumulation function, knowing where that came from, spending 3 weeks knowing where that came from. But we did like I said, we did the heavy lifting. We've earned the right to just write it down. Now the reverse process is everything. So you have the exact accumulation and you want exact rate of change. And again, we want to have a fast track for that. So to introduce this reverse process, we have a sphere context. And so now we have the accumulation function, and we're going to start by looking at those fixed delta x, so those fixed h values. And we're going to build this, so that we're going to build an approximate accumulation function from the exact accumulation. And that's what that looks like. It uses the left x. And then from that, we're going to build an approximate rate function. And that's what that looks like. And so having h and left x in there is a little problematic. But it's still a good transition point, serving from the transitioning from the forward and using left x again, right? So using left x that we built before. And so the question is, how are we going to get exact rate of change? And this method isn't going to work. So we kind of start over and we say, let's look at doing this instead. So the black is our old method of using fixed intervals. Let's look at every interval h. Every interval h rather than just the discrete intervals. And then rather than fixing x and letting h vary, we want to think about, we're building the function, right? So we want h to be constant and we want x to vary. So we have approximate rate function for a given h. And then we want to let h, again, we're going to let h get small. Every time I let h get smaller, I'm going to get closer and closer to exact accumulation until the approximations are essentially the same to each other, and then we know we've landed on the exact accumulation. So we're not going to use the limit notation. We're going to always use this notation. It can mean approximate rate of change or exact rate of change when h is small or small enough. And so we're going to look at closed form accumulation next and rate functions. So thus far, the accumulation functions we did in the integral derivation of integral, those were represented in open form, integral form only. So it's a really nice form for representing the meaning, but open form is not nice for computing, right? And so it's through developing the derivative rules for finding closed rate functions that we can then go back and say, okay, when we find these derivatives in closed form, Well, now every time you find a derivative in closed form, you've actually found an accumulation function in closed form as well. So we're gonna leverage. We're gonna do the derivative rules for the power rule, the product rule, the quotient rule. We're gonna leverage those to start building our inventory of accumulation functions in closed form, which we didn't do before. So here's this idea. So in one part of the course, we look at x squared, and we derive that the rate of change is 2x. So closed form accumulation, closed form rate. But so now that means that we can represent that original function as an open form accumulation function. So that means we've learned something else. So now we know what the closed form of that open form accumulation function is. So that if we have that open form accumulation function, now we know from the derivative rules that can be written as a closed form as x squared. So we have that do that. Just what's that same process or thinking for the volume of a sphere? Okay, applications of rate functions, second derivatives, curve sketching, related rates, optimization. So this is it feels a little more like the traditional course, except we're just going to keep the focus on rate of change function, accumulation functions. We're really going to train them to understand the problem, model, and represent. And then at the end of the course, the fundamental theorem of calculus is the culmination of most of the work in the course. It's built on our exact net accumulation function, our rate of change from accumulation, so derivative, and then the derivative rules leading to knowing closed forms for integral functions, antiderivative. So all that work that we did is really builds the fundamental theorem of calculus. So we have a circle of functions here. If we start with an amount function, then its rate of change function is our difference quotient for small h. And the exact net accumulation function then can be written in terms of that rate function as an integral function. And then we can come back and write the total amount function in open form as f of a plus that net accumulation function. And so that's our total amount function in open form. If we subtract f of a from both sides are expressing exact net accumulation or amount of change, but in two different ways. This side is expressing it as final minus initial, and this side is expressing it as accumulation of sum of bits of change, but they're both expressing net accumulation. And so that's our fundamental theorem of calculus, which we worked all semester to build. So it expresses the net accumulation function or amount of change in two ways, as an accumulation of bits of change and as final amount minus initial amount. And then the right side allows us to write these open form accumulation functions in closed form, a computable, easy computable form, knowing antiderivatives. So from derivatives, we know antiderivatives, and we can write the closed form. And so I just want to mention one more thing. Area. So then area is just one of many applications of accumulation. So we don't talk about integral as intrinsically area bounded by the curve, but area bounded by the curve is just one of a zillion quantities in the world that we can model its accumulation of. So I have more, but my time is up.